And the talk will be essentially structured in 4 parts. So first I will recall the definition of conditional flat functor and relate it to categorical Galois theory and show that in nice algebraic categories, actually they correspond to this admissibility condition to have a Galois theory. In the second part, I shall give a criteria to determine if there are fiberwise localizations in an algebraic context. The third part will be about Birkhoff subcategories that give plenty of examples of conditionally flat functors. And finally, I will concentrate on one example of an adjunction between double groupoids and 2 groupoids in a Maltsev category. So, conditionally flat functors appeared in the study of pullback preservation properties related to homotopical localization functors. And the paper that inspired this work was by Dror Farjoun and Jérôme Scherer. And basically, after investigating some properties of vibration sequences of pointed topological spaces, they consider some questions in the category of groups, but concerning short exact sequences instead of vibration sequences. So in order to explain what a conditionally flat functor is, let me tell you first what a flat short exact sequence is. So if C is a pointed category with a 0 object and L is an endofunctor, then the exact sequence KEB is called L flat if it is sent by the endofunctor L to an exact sequence L of K, L of B, L of B. So it's just preserved by the endofunctor. And then Farjoun and Scherer call conditionally flat an endofunctor if L flat extensions are pullback stable. So it's a very natural condition. And explicitly, this means the following. If you have a short exact sequence KEB and you pull it back along any map F, so this P is actually the pullback of P along F, then if the lower short exact sequence is preserved by L, then also the red upper short exact sequence should be preserved by L. Now, any reflective subcategory of a pointed category naturally gives localization by using the terminology of homotopy theorists. Actually, it's an idempotent monad, but what they mean by localization is an idempotent pointed endofunctor. And many examples they give of conditionally flat functor that occur actually in the category of groups, the group varieties. So any subvariety of the variety of groups will give an example of a conditionally flat functor. And we wanted to understand why this is the case and why in other semi-abelian categories they are more rare than in the variety of groups. So given L and a short exact sequence KEB, in the category of groups, one can always build a commutative diagram like the one here in the center, where eta k is the k component of the natural transformation eta from the identity to the localization L, and E is a morphism that is inverted by the localization. This construction is given in a paper by Casacuberta and Deschemacher. And so one says in a pointed category, C, that L admits a functorial fiberwise localization if one can build such a diagram, where the diagram is exactly the same we had in the category of groups, and eta k is the k component of what they call the co-augmentation. And if you think in terms of localization induced by an adjunction, to be just the unit of the adjunction, and E is inverted by L. And one asks that this construction should be functorial. Now, in groups, this property actually is related to the fact that take the kernel of the unit of the adjunction, eta k, so that the kernel is called Tk. It is not only a normal subgroup, but it is a fully characteristic subgroup of K. And we shall see that this condition actually is very important to get conditionally flat functors in any homological category. So, What is a homological category? It is a regular category, so you have the regular AP monofactorizations that are pullback stable. It is pointed, and it is protomodular in the sense of Bourne, which means that the split Shor-5 lemma holds in C. So this definition is due to Bourse and Bourne, and they called it homological because the main homological lemmas, like the snake lemma, 3x3 lemma, are known to hold in this context. And we have plenty of nice examples. We have groups, of course, and rings, associative algebras, Lie algebras, heightened semilattices, loops, or cross modules. All these are examples of varieties of universal algebras, so these categories are not only homological, but they're also semi-abelian in the sense that are bar exact. And then we also have co-commutative Hopf algebras, topological groups, C-star algebras, the dual of pointed sets, or any regular additive category. Now, an important proposition of Dominique Bourne that we shall use in the only proof I will give during my talk is the following. If you have a commutative diagram like this one in a homological category, then the square A will be a pullback precisely when the restriction to the kernels is an isomorphism. And this has also given opportunity to give an alternative definition of protomodular category. Now, the first result is related to a full regular epireflective subcategory of a homological category C. So C is homological, and X is a reflective subcategory such that each component of the unit of the adjunction is a regular epi that admits a functorial fiberwise localization. For instance, C could be groups. And then the following conditions are equivalent. L is conditionally flat, or the localization L preserves any pullback of this shape. So here, G is a regular epi between objects that lie in the subcategory X of C, so they are local objects, and eta C is just the unit of the adjunction. So I will prove this simple result. Assume that L is conditionally flat. And let us prove that L preserves all these pullbacks of the form P, where G lies in the subcategory X. So what we have to do is to take the kernels, or extend the diagram by taking the kernel of G, which is also the kernel of P2, because P is a pullback, and observe that the lower sequence is certainly L flat, mainly preserved by L. And this is because it lies in the subcategory X of C. G by assumption, and the kernel of G, because being a regular epireflective subcategory, it is closed under subobjects in C. So, by assumption, we know that L-flat extensions are pullback stable, so the upper sequence, the red one, is also L-flat. And so we get here a commutative diagram where, when we apply the localization, where both rows are exact. And by both result that I mentioned before, since C is a homological category, if we have an isomorphism at the level of kernels, then on the right-hand side you have a pullback. And this proves too. So the other direction, there are two steps. The first one is a bit longer, so I will just say what it consists of. Given an L-flat exact sequence, by using this fiberwise localization of L, one can reduce the problem of the special case where the kernel of the extension actually lies in the subcategory X of C. Then, in the second step, one considers a pullback alpha of an L-flat extension along any morphism F. So, by the first step, we know that K can be assumed to be in the subcategory X. So the eta K here will be just an isomorphism. And again, by Bourne result, we deduce that this is a pullback. So, the point is this preservation of pullbacks. So on the left-hand side, we have a rectangle of alpha and beta. We have just observed that are both pullbacks. And we want to prove that L preserves this alpha plus beta rectangle. But the alpha plus beta rectangle is also obtained by factorizing F followed by eta V on the left-hand side as eta X followed by LF on the right-hand side, and then pulling back the composite along L of P. So if we look at the lower square on the right, we see it's a limit of local objects. So it's again in the subcategory. Of course, it will be preserved by the localization. Whereas the upper square on the right is exactly on the form we know that the localization preserved pullbacks. So it's the form P. So both these squares are preserved by L. So L of alpha plus L of beta will be a pullback. And of course, if you look on the left, beta will also be preserved by the localization because you have vertical maps that will be inverted. So we are essentially done, because if we have both L alpha plus L beta and L beta that are pullbacks, then by the usual associativity of pullbacks, you deduce that L of alpha is a pullback. We know that the lower sequence is exact. L of alpha is a pullback. And so we are done. We conclude that the upper sequence in the diagram is necessarily exact, showing that the localization is conditionally flat. So it's exactly the same property as preserving this type of pullbacks. One would wonder, why is this important? It is important because it is related to Galois theory. And actually it is well known that a full reflective subcategory X of a homological category C is admissible for the class of regular epis in the sense of Galois theory, Jean-Elitz and Kelly, precisely when the left adjoint F preserves the pullbacks of type P. So this conditionally flat condition is actually what guarantees the existence of a classification theorem for extensions related to an admissible Galois structure. So this is exactly what I write here. But provided, of course, that the category C is homological. It will not work in topological spaces. It's an algebraic proof. So if you admit functorial fiberwise localization, admissibility for categorical Galois theory is equivalent to the fact that the localization is conditionally flat. So a natural question then is to determine when one can find these functorial fiberwise localizations. And the second result here says that if you have a homological category and L is a localization induced by an adjunction, then C admits a functorial fiberwise localization with respect to L if and only if a very simple property holds. Namely, if you have a normal mono K and you push, and you consider the K component of the natural transformation from the identity to the localization, then the push out exists and it is a pullback. And another equivalent way of expressing the property is to ask this property M, which says that if you have a normal mono K, then you precompose this K with the kernel of the K component of the unit of the adjunction, Tk, then the composite is again a normal monomorphism. You know that the composite of two normal monos is not a normal mono in general, but if this holds, then you will have the existence of fiberwise localization. So in abelian categories, of course, this is trivial, because if you compose two monomorphisms, you get a mono, which is always a normal mono. So this condition is always satisfied in the abelian world, so you don't see it. In groups, it's easy to check that, as I said, that Tk is actually a fully characteristic subgroup. So this implies that this composite Tk followed by K is again a normal subgroup. So condition N is satisfied, and this categorically explains why we have so many examples of fiberwise localization in the category of groups. The same argument as in groups is true also in topological groups and in compact groups. In co-commutative Hopf algebras, there is a similar argument. So if you take K, which is a normal subalgebra of a co-commutative Hopf algebra E, then you can define the function phi E that sends any K in K to E1 K S of E2 by using the Sweedel notation, and S is the antipode of your Hopf algebra. But this is not only a function, it is a Hopf algebra morphism. So by functoriality of the localization, actually phi E restricts to Tk. And this means that if you take K in T of K, then this element will be again in Tk. And so the property N holds, so that co-commutative Hopf algebras also admit functorial fiberwise localization with respect to any L. One localization could be the abelianization, so going from co-commutative Hopf algebras to co-commutative and commutative Hopf algebras, for instance. So one might expect that a similar result would also hold for the category of cross modules. Why? Because all the examples I gave so far are examples of internal groups. So in sets, in topological spaces, compact algebra spaces, or in co-commutative coalgebras, because Hopf algebras can be seen as groups inside co-commutative coalgebras. And the category of cross modules is known to be equivalent to the category of internal groups in CAT. So we are in a similar situation. But actually, quite recently, Mongeon, Scherer, and Stepp, they proved the category of cross modules does not admit functorial fiberwise localization in general. So they give an example of a reflective subcategory, which is given by those cross modules of the form A goes to 0, where A is abelian, and they show that the condition N is not satisfied. So it's a different situation. Where we shall find many examples of conditionally flat functors is in the context of Birkhoff subcategories. So let me just recall that a regular epireflective subcategory of a regular category is Birkhoff if it is closed also under quotients. So if f from x to y is a regular epi with the domain in x, then also the codomain belongs to the subcategory. And of course the name Birkhoff comes from Birkhoff's theorem. Any subvariety x of a variety C of universal algebras is a Birkhoff subcategory by the HSP theorem. And the subcategory of profinite groups inside the category of compact Hausdorff groups is another example. And as I mentioned before, commutative and co-commutative Hopf algebras inside co-commutative Hopf algebras is a Birkhoff subcategory as well. And if we assume that our homological category also satisfies an additional condition, namely that normal monos are stable under regular images, that I will call ID for ideal determined, because it is the crucial axiom in the definition of ideal determined category. So this means the following: if you have a commutative square like this one, and K is a normal mono, K prime is just a mono, and the vertical morphisms are normal epis, then you can conclude that K prime is again a normal mono. Then we can prove actually that any Birkhoff subcategory of a homological category C satisfying this ID gives a conditionally flat functor. So all semi-abelian categories satisfy this condition. So if you add exactness to homological axioms, you get also a result. And the idea is based on this ID property, ideal determined property, and the fact that the co-kernel of a morphism in X is computed in X exactly as it is in C. Now, in the last 5 minutes, I will just give an example of a Birkhoff subcategory in the category of double groupoids. So, recall that one calls a category Maltsev if any reflexive relation C is an equivalence relation. So, in particular, all the examples we have considered before of homological categories are Maltsev categories. It's a more general context. Now, when C is a regular Maltsev category, the category of internal groupoids in C is again regular Maltsev. This is very different from sets, because groupoids is not a regular category in sets. But if the category C is regular Maltsev, then the regularity survives to the internalization. So you can iterate this and take double groupoids in C, which will be again a regular Maltsev category. Now, two groupoids can be seen as a full subcategory of double groupoids whose objects have a discrete vertical structure. And the result with Nadia Egner is that when you have a finitely co-complete regular Maltsev category, then two groupoids is a Birkhoff subcategory of double groupoids in C. And I shall now just explain how the reflector works in this Maltsev context. So if you start with a double groupoid, which is depicted behind, so X, then you take the co-equalizer eta 0, 0 of D0 and C0, and you take the discrete groupoid on the quotient Q 0, 0. You can think of this as kinetic component of the groupoid X0, 1. Then you push out this quotient eta 0, 0 along the morphism E0 that gives the reflexivity of the groupoid X1, 0. So that is the horizontal groupoid of the double groupoid. So you push out and you get this object Q0, 1. And you do the same on the other side. So you push out this quotient along eta 1, which gives the reflexivity of the groupoid X1, 1 with object of object X0, 1. So you get a double reflexive graph with induced morphism. And since each component of this eta, eta 0, 1, and so on, is a regular epi, this double reflexive graph is underlying a unique structure of double groupoid, which is also a two groupoid, because here you see we have a discrete groupoid. And so this is the reflection. By construction, you see it's a regular epi-reflective subcategory, because you're just doing quotients, and it's obvious that it's closed under regular quotients inside double groupoids in C. So in particular, one can consider Maltsev varieties. So a variety of universal algebras is a Maltsev category if and only if it has this famous ternary term, P of x, y, z, satisfying the Maltsev identities. And when C is a Maltsev variety, then two groupoids inside C is again a Maltsev variety. And the reason is that double groupoids is known to be a Maltsev variety. We have just proved that two groupoids in C is a Birkhoff subcategory of this variety, which means it's a subvariety, so it's itself a variety of universal algebras. And so the last question I want to mention here is, do we have an equational representation of this variety of two groupoids in a Maltsev variety? First, recall that a double groupoid like the one in the picture can be also presented as a single Maltsev algebra X11 equipped with 4 endomorphisms ST, UV, satisfying so this first line of identities that are simply expressing the fact that this is a double reflexive graph, plus two commutator conditions where EQ of S is just the kernel pair of S and EQ of T is the kernel pair of T, and delta X11 is the smallest equivalence relation on this object. So this is a presentation of the Maltsev variety of double groupoids, and by adding some identities here, expressing its two groupoid, not only a double groupoid, we get a complete characterization of this Maltsev variety. Given any C, we can give a presentation of the variety of internal groupoids. Last result, so if C is semi-abelian, then the localization from double groupoids to, in double groupoids, that corresponds to reflection to two groupoids is a conditionally flat functor. So, the final remarks. There are some parallel concepts in homotopy theory, conditionally flat functor, and in category theory with the notion of admissible reflection for Galois theory that coincide in some good algebraic structures. The property of functorial fiberwise localization is also useful to characterize torsion theories. I have not developed this part of the work, but it's known that regularly reflective subcategories in an abelian category are torsion-free if and only if they are closed under extensions. And this same result still holds in non-abelian context with when you have the functorial fiberwise localization. Now, higher categorical structures in Maltsev categories provide new examples of Birkhoff subcategories, and I recommend this nice article by Arnaud de Vieussard, where he studied the reflection from simplicial objects in a Maltsev category to groupoids, which is a Birkhoff reflection. And finally, this adjunction that I mentioned in the last example opens the way to some results in non-abelian homological algebra, because When you have admissibility, you can study homology and Hopf formulas, and some of these developments will be presented by Nadia Egner later on at 5 p.m. In her talk. So thank you for your attention.
Thank you, Marino. Are there questions or comments?
Richard.
You said that if you've got a Birkhoff subcategory or homological category shows that normal monos are stable under images, then the localization function is conditionally flat. Is it also true that it has these functorial fiberwise localization? That wasn't.
No, it's not true. The counterexample in cross modules gives a counterexample to this statement. The one that Mongeon, Scherer, and Sterk found, yes.
So the proof is just different?
Yes. Yeah. Yes, Clément.
What's the difference between a homological category, which is ideal determined, and the semi-abelian category?
Well, actually, if you add idea determined to homological category, you get exactness. So it's the same. It's always this discussion about the existence of binary coproducts, which is included in both definitions of ideal determinant and semi-abelian. But what you really need here is just homological plus bar exact or ID. But without coproducts. We don't really need the binary coproducts. So the answer is yes, you get the same thing. Yeah. Yes, sorry, but I owe you an explanation. Why didn't I write semi-abelian? Thank you for the question. And the reason is that you can prove it in ideal determinant without protomodularity. So for the simplicity of the presentation, I didn't want to introduce new notion. I said, let's add ID, and it will work. But actually, if you only have ideal determinant without semi-abelian, without protomodularity, the same result holds. Thank you.
Are there more questions or comments? You're better than me. Yes.
I remember, so this counterexample in cross modules by Mongeon, Scherer, and Sterk. I remember discussing this with Florence, and she said to me that this is the first condition, categorical conditions she knows, which is not satisfied in cross modules, but it is in groups. And she asked me, do you know other conditions which distinguish those two categories, groups and cross modules? Do you know any kind of conditions like that?
Well, I don't actually, but there might be some very specific conditions that I've not looked at that are satisfied by groups but not by cross modules. But this is, in my work, the first time I encountered this situation. Yes.
You mentioned that if you have a multiple category, then a regular multiple, the group points in it will be regular. Is it also true if you just take categories in general to a regular multiple?
But yes, it's true because categories and groupoids coincide in a multiple category. Yes, so that's an advantage. And actually, this regularity result also holds for Groussa, what we proved with Diana Rodello, which is slightly more general context. Instead of having two permutability, Rs equals Sr for any pair of equivalent relations, we have three permutability. But if you go to 4, it doesn't work.
There's someone here.
So I have a question that this fiberwise functorial localization, is there any connection with localization of the category? Like, is there any relation between localization of the category and what you talking about fiberwise functorial localization?
So this notion was used for vibration sequences in topological spaces. Now it's all about inverting maps. So it's connected in the sense that also the condition of fiberwise localization was not invented in algebra, but it came from algebraic topology. And they ask exactly the same condition for vibrations with homotopy fiber to be preserved by the localization. So there is a connection in the sense that we are interested in which morphisms are inverted by this process of localization.
Subgroups of free groups are free, and this is not true for
That's true.
groups.
Yes, and we encountered that together for the first time. Thank you for reminding me.
Are there extra comments or questions? So if not, we thank the speakers.